Imagine trying to fix a bug in a single file of code that is 50,000 lines long. Because every part of the program is tangled together, changing one line can cause a breakdown in an entirely unrelated section. It is nearly impossible to read, let alone test or maintain. This is why we use modular design. Instead of building one massive program, we divide the system into smaller, self-contained parts called modules. Each module acts like its own machine, responsible for one specific task, like handling logins or processing payments. But dividing the code is only the first step. If a software system is broken down into 100 separate modules, how do engineers determine if those modules are actually designed well? Simply splitting code into files doesn't guarantee quality. Without specific metrics to evaluate how those modules interact, even a modular system can become too complex to manage, leading to wasted development time and frequent bugs. Software engineers use two key metrics to measure quality. The first is cohesion. Cohesion measures the internal strength of a module by looking at how closely related the tasks are within that single component. Think of a hospital department. A highly cohesive heart department contains only cardiologists, nurses, and ECG machines. Everyone has one shared purpose. In contrast, a department that mixes heart patients, billing desks, and food delivery services has low cohesion. It is disorganized and difficult to manage. In software, a highly cohesive login module works the same way. Every function, from validating the username to verifying the password, is strictly related to the login process. The module has one well-defined responsibility. If we force this same module to handle unrelated tasks like processing payments or printing invoices, cohesion drops. The module is no longer focused, making the code harder to understand and more prone to errors during updates. High cohesion makes code predictable. When a specific bug occurs, developers know exactly which module to open, as the related logic is contained in one isolated location. The second metric is coupling. While cohesion looks at the inside of a module, coupling measures the external connection between different modules. It describes how much one module depends on another to function. If modules are heavily dependent on each other, they are highly coupled. In this state, modifying a single module can trigger a chain reaction of errors across the entire application. This makes the system fragile and difficult to change. Low coupling is the preferred alternative. In a low-coupled system, modules operate independently and only share the absolute minimum amount of information required, such as a login module passing a single user ID to a dashboard. To keep these straight, remember, cohesion refers to what is close and inside a module. Coupling describes how a module connects to the outside. Let's test this intuition. Look at this blueprint for an ATM system. The receipt printing module is directly manipulating the internal logic of the cash dispenser. Based on our metrics, what is the design flaw here? This is a clear case of high coupling. A receipt printer should only receive data to print. It should not have the authority to control how cash is dispensed. This unnecessary dependency makes the software rigid and harder to test. Professional modular design aims for a specific combination of these two metrics, high cohesion and low coupling. This approach ensures that every module is focused and strong on the inside, while remaining independent and minimally connected on the outside. Comparing the two shows their different roles. Cohesion focuses on the internal relationship within one module, where higher is better. Coupling focuses on the external relationship between different modules, where lower is better. When both metrics are optimized, the software becomes easier to maintain. Testing is faster because modules have single responsibilities, and code becomes more reusable because independent modules can be moved to new projects without bringing along a web of dependencies. Balancing these metrics is a core requirement for building professional, scalable systems. With this foundation, we can now examine the specific categories of cohesion used to evaluate code in the next part.